What type of microscopic structure does barium fluoride have? Well, barium is a metal and fluoride is a non-metal. So that would suggest ionic. And if you do the electronegativity difference, it also comes out to be more than 1.5-ish. And therefore, ionic crystal lattice seems to make some sense. Covalent would be between two non-metals, and metallic would be between two metals. Atoms in a molecule are held together inside the molecule. The atoms of a molecule are held together by covalent bonds. The bonds between atoms within the nitrate ion can best be classified. So now we're inside the nitrate ion, which means that we are sharing electrons. The nitrogens and the oxygens are doing that, and therefore it's non-metals, and so those can also be described as covalent bonds. But now we've got two types of covalent bonds here, and the one is polar and the other one is non-polar or pure. And because this lands up with the polarity of a negative ion, you're going to land up with this being a polar covalent bond. Part of it remains negative. It's got extra electrons. The predominant intermolecular forces present between solvent and solute particles in a solution of magnesium chloride and water. So the water is going to be polar covalent, and the chlorides are going to be negative, and they will be attracted to the slightly positive, and the magnesium 2 pluses are going to be attracted to the slightly negative oxygen. So that is an ion dipole intermolecular force. Which one of the following statements about the heat of the reaction is incorrect? So, the heat of the reaction is the average kinetic energy of the system. No, that is got to do with enthalpy, and it's not even enthalpy directly. The heat of the reaction is the products minus the reactants. That's true, the energy of the products minus the energy of the reactants. Heat of the reaction, sorry, that should be reaction. It can be positive or negative, that is true. And the heat of the reaction is the net change of chemical potential energy of the system. Yes, that's the difference between the products and the reactants. So A is the only incorrect option. We've got a Maxwell-Boltzmann energy distribution here, and shows the number of particles as a function of the kinetic energy of the reaction at 4 different temperatures. The minimum kinetic energy needed for effective collisions is represented by E. Which one of these curves represents the reaction with the highest rate? Highest rate means most effective collisions. In other words, it needs to have lots of particles with lots of energy. And the one with the most energy is this one over here, where you have got lots of particles that have more energy than E. If I take a look at C's curve, that's far fewer particles. If I take a look at B's curve, that's even fewer particles with that amount of energy. So your highest temperature is D. And A, by the way, didn't even have any particles that landed up with enough energy to react. The series of experiments with 0.5 gram samples of magnesium were added separately to 100 centimeters cubed of hydrochloric acid. The table below summarizes the experimental conditions. So we get the same volume of hydrochloric acid, the same mass of magnesium, but we've got ribbon versus powder, different concentrations and different temperatures. In which of the experiments will the magnesium be expected to take the shortest time to react completely with excess hydrochloric acid? So the first one is powders obviously are going to react faster than ribbons. The next one is that highest concentrations will react fastest. And finally, highest temperatures will react fastest. So we land up in a situation where this is powder and high temperature. This is powder and high concentration. So 3 and 4 seem like the most likely ones to have the highest reaction rates. Which of the following is the strongest reducing agent? I decided to take this question out. You need to use the redox table, and we haven't really used that very much. It turns out that it is magnesium, because if you look at the redox table, it is the most likely to be oxidized. It is highest on that redox table. Consider the following redox reaction. The oxidizing agent is, so you now need to assign oxidation numbers to everything, and we land up with -2 plus 7 minus 2. This turns out to be plus 7, which is a bit weird for chlorine, but it is how it is. Minus 2, sorry, that's plus 5, because that has to add up, so it's minus 2, so it's minus 6, plus 5 equals minus 1. Plus 1, over here you've got minus 2, this turns out must be plus 8 if it's going to be neutral. This manganese plus 4, at least minus 4, plus 4, minus 2 plus 1. Okay, so what have we got as changes? We've got the manganese going from plus 7 to plus 4, that's, it's reduced. And you've got chlorine going from plus 5 to plus 8, so that is oxidized. And then the oxidizing agent is the substance that got reduced, so it will be the MnO4 minus. There are some weird ones in here, but you actually need to be able to deal with weird ones every now and again. The reaction represented by the equation below takes place in the presence of a catalyst. You've got a big organic molecule, breaks up into smaller organic molecules. We call that, the process is called cracking. And you land up giving off some hydrogens at the same time.